Hello everyone. Today, we will be discussing an important concept in CMOS logic design, the evaluation of K-equivalent for series and parallel transistors. Now, why is this topic so important? When we design CMOS circuits, whether it's a simple inverter or a more complex AOI or OAI structure, the sizing of transistors directly impacts speed, power, and reliability. The term K here refers to the transistor conduction parameter, which depends on mobility, oxide capacitance, and the width-to-length ratio of the MOSFET. In CMOS circuits, transistors are often connected in series or in parallel, forming pull-up and pull-down networks. To analyze the current drive and delay of such networks, we need to determine an equivalent K value that represents the combined effect of multiple transistors. This evaluation simplifies our analysis and helps us estimate important performance metrics like switching speed, propagation delay, and power dissipation. Now that we have understood how the pull-down and pull-up graphs are constructed, let us move forward and see how these concepts are practically applied in implementing Boolean functions. This brings us to the idea of combinational CMOS logic circuits. A combinational circuit is essentially a logic network where the output is determined solely by the current values of the inputs, with no memory or feedback involved. In mathematical terms, we can say that the output is a direct function of the inputs, represented as output equals F, inputs. To realize such Boolean functions at the transistor level, we use series and parallel connections of MOS devices. When NMOS transistors are connected in series, they collectively conduct only when all the input conditions are satisfied, which directly maps to the logical and operation. Conversely, when NMOS devices are placed in parallel, current can flow if any of the input conditions is true, which maps to the logical or operation. The complementary nature of CMOS design further enhances this representation. For every NMOS pull-down configuration, there exists a dual PMOS pull-up configuration. This ensures that whenever the pull-down path is active, the pull-up is inactive, and vice versa, thereby guaranteeing correct logic evaluation. In this way, CMOS combinational logic elegantly combines Boolean algebra with physical transistor connectivity, resulting in compact, power-efficient, and logically complete digital circuits. This structured approach is the foundation of realizing more complex gates and eventually entire digital systems. Before diving into CMOS logic circuits, let's recall the analogy from passive networks. In resistors, series connections add up resistances, while parallel reduces the effective resistance. In capacitors, the rule is inverted: series reduces effective capacitance, parallel adds them. Now, when we move to transistor-level CMOS logic, similar principles apply. NMOS and PMOS transistors act as controllable switches. A series path of transistors corresponds to a logical and because all must conduct to establish a connection, while a parallel path corresponds to a logical or since any conducting device completes the path. This analogy from R&C networks makes CMOS logic structures much more intuitive. In CMOS logic, the NMOS network forms the pull-down path, while the PMOS network forms the pull-up path. NMOS devices conduct only when the input is high. So, when NMOS are placed in series, all inputs must be high for conduction, implementing an AND. In parallel, any high input can pull the output low, realizing an OR. PMOS devices are complementary, they conduct when input is low. So, series PMOS act like OR gates, while parallel PMOS behave like AND gates. This duality between NMOS and PMOS guarantees full logic functionality, ensuring that exactly one of the networks establishes a path to VDD or GND for valid logic levels. To implement a Boolean function in CMOS, we construct the NMOS pull-down network directly from the function, while the PMOS pull-up network is its exact De Morgan dual. For instance, if our function is f equals AB plus C, then in the NMOS pull-down, A and B transistors are placed in series, and that branch is paralleled with C. The PMOS pull-up is its dual, A and B in parallel, combined in series with C complemented. This ensures that when the pull-down conducts, the pull-up is blocked, and vice versa, giving us rail-to-rail logic levels. Continuing from the discussion on combinational CMOS circuits, let us now narrow down to the concept of basic CMOS gates, which form the building blocks of all digital logic. In CMOS design, every logic gate is realized by combining two complementary transistor networks. The first is the pull-up network, implemented using PMOS transistors, and the second is the pull-down network, implemented using NMOS transistors. These two are always arranged in what we call a complementary topology. The significance of this arrangement is that it guarantees proper rail-to-rail logic operation. Whenever the output needs to be driven to a logic high, the pull-up network turns on while the pull-down network remains OFF, thus connecting the output to VDD. Conversely, when the output needs to be logic low, the pull-down network activates while the pull-up network switches OFF, tying the output to ground. This complementary action ensures that the output is always a clean digital level without undefined voltages, and also prevents static current from flowing directly between VDD and ground. From a logical perspective, the connectivity of transistors directly maps onto Boolean operators. When transistors are arranged in series, current flows only if all devices are on, which corresponds to an AND operation. Similarly, when they are arranged in parallel, current can flow if any one transistor is on, which corresponds to an OR operation. This fundamental mapping provides us with a systematic method to design any Boolean function at the transistor level. Thus, CMOS gates not only deliver full-swing, low-power logic but also offer a direct hardware interpretation of Boolean algebra through their pull-up and pull-down duality. This property is what makes CMOS the dominant technology for building both simple and highly complex digital systems. Each MOS transistor is characterized by its drive factor, K, which depends on carrier mobility, oxide capacitance, and device geometry W divided by L. In logic analysis, we often normalize Cox and express strength through W/L. In series connections, the effective conductance is like resistors in series, so we take the reciprocal sum to compute equivalent K. In parallel connections, the strengths simply add. This calculation helps us determine relative delays and rise/fall asymmetries in CMOS logic circuits. Let us work through an example. Consider F equals AB, which in CMOS is implemented as a NAND gate. The NMOS pull-down consists of A and B in series, while the PMOS pull-up consists of A and B in parallel. Suppose the NMOS has W equals 10 and L equals 10, so its drive factor is 1. The PMOS has W equals 20 and L equals 15, giving K is almost equal to 1.33. For the series NMOS path, the equivalent conductance is the reciprocal sum 1/1 plus 1/1 inverse, which equals 0.5. For the parallel PMOS, the conductance is add, yielding 2.66. This clearly shows the asymmetry. The pull-up is stronger than the pull-down. Such calculations are crucial in logic design because they reveal whether the switching threshold will skew and whether sizing adjustments are needed for symmetric rise and fall times. Continuing from our discussion on mapping complex CMOS logic to an equivalent inverter representation, let us now analyze the case of a NOR gate. In the pull-down network of the NOR gate, the NMOS transistors are connected in parallel. For parallel NMOS, the effective strength factor is simply the sum of their individual Kn values. Hence, if each transistor has a drive strength Kn, the total becomes 2 knots. On the pull-up side, the PMOS devices are connected in series. In this case, the equivalent strength factor is reduced because current conduction is restricted through a longer effective channel length. The formula for series PMOS gives us Kek_P equal to Kp divided by 2. Therefore, the NOR gate can be modeled as an equivalent inverter where the NMOS has strength 2 knots and the PMOS has strength Kp/2. This mapping is extremely useful as it allows us to compare switching thresholds, balance pull-up and pull-down strengths, and verify symmetry of the design at the inverter abstraction level. Now, let us consider the NAND gate. Here, the pull-down network has NMOS transistors in series. In the series connection, the conduction path behaves as if the effective channel length is doubled, thereby reducing the drive strength. Thus, the equivalent Kn becomes Kn divided by 2. On the other hand, in the pull-up network, the PMOS transistors are connected in parallel. For parallel PMOS devices, the effective strength is the sum of individual strengths, leading to Kek_P equal to 2 Kp. Similar to the NOR case, we can replace the NAND gate with an equivalent inverter that has Kek_N equal to Kn/2 and Kek_P equal to 2 Kp. This abstraction provides a powerful way of analyzing delay, noise margins, and switching points without going into full transistor-level analysis every time. In summary, CMOS logic structures are systematically built from NMOS and PMOS series/parallel combinations, mapped from Boolean functions. Series connections implement AND, while parallel implement OR, but NMOS and PMOS follow complementary logic. By calculating the equivalent K values of these structures, we quantify strength and predict delay characteristics. Finally, careful device sizing balances pull-up and pull-down strengths, ensuring symmetric switching thresholds and optimized performance. Continuing our discussion on CMOS logic realization, after understanding the complementary principle of pull-up and pull-down networks, let us now analyze the working of a two-input NOR gate in CMOS technology. In the case of the pull-up network, which is composed of PMOS transistors, conduction occurs only when both inputs are logic 0. Since PMOS devices turn on at 0, the only way the pull-up can drive the output high is if VA and VB are simultaneously 0. This condition requires a series configuration of PMOS devices, because both must be on together for the current path to connect the output node to VDD. On the other side, the pull-down network consists of NMOS transistors, and here the situation is complementary. NMOS devices conduct when the input is logic 1, so the output node is pulled low whenever VA or VB equals 1. This corresponds to a parallel configuration of NMOS transistors, since the presence of just one active device is sufficient to establish the conduction path to ground. From this configuration, it becomes clear that the CMOS NOR gate is realized by combining a series PMOS pull-up structure with a parallel NMOS pull-down structure. This dual relationship between the two transistor networks not only ensures that the gate realizes the NOR functionality, but also maintains the fundamental property of CMOS logic. At any given time, either the pull-up or the pull-down is active, preventing direct current flow from VDD to ground, thereby ensuring low static power dissipation. This implementation also highlights how Boolean expressions are naturally mapped onto transistor arrangements. For the NOR gate, the pull-up corresponds to the N of the inverted inputs, while the pull-down corresponds directly to the OR of the true inputs. Such mappings form the backbone of CMOS circuit design and will be the guiding principle as we extend our discussion to more complex gate structures. Building upon our understanding of the CMOS NOR gate structure, let us now move one step further and look at how we model its behavior in terms of equivalent inverter characteristics. Earlier, while analyzing the inverter, we studied how the critical voltages, especially the threshold voltage VTH, determine the switching point. What makes this important is that VTH is not a fixed property, it can be influenced by the sizing of the transistors. When we extend this reasoning to more complex gates such as the NOR, we use the technique of reducing the gate into an equivalent inverter model so that the well-understood inverter behavior can still guide our analysis. Now, when we examine the transistor arrangement inside the NOR gate, we encounter two distinct configurations: series connections and parallel connections. Let's first consider the case of series transistors, as we saw on the PMOS side of the NOR pull-up. Conceptually, current must pass through two consecutive channels, each introducing its own resistance. If the transistors are identical, the net resistance effectively doubles, which means the drive capability or transconductance is halved. Therefore, two transistors in series can be approximated as a single equivalent transistor with K equal to K divided by 2. In contrast, when transistors are arranged in parallel, as in the NMOS pull-down of the NOR, the current paths add together. This allows the combined structure to conduct roughly twice the current of a single transistor with the same gate bias. Hence, the parallel configuration is modeled as an equivalent transistor with K equal to 2K. This equivalent modeling approach is extremely powerful because it allows us to analyze complex logic gates without dealing with every individual transistor's current equation. Instead, we reduce the gate into a simpler inverter-like structure and capture its effective switching properties through equivalent transconductance values. This not only simplifies our hand analysis but also provides insights into the impact of sizing, stacking, and parallelization of devices in determining speed, power, and robustness of CMOS logic circuits. Continuing further, after analyzing the two-input NOR gate, we now generalize the design to an n-input CMOS NOR gate. The principle of construction remains the same, but the configuration of transistors in the pull-up and pull-down network scales with the number of inputs. In the pull-down network, which uses NMOS transistors, the arrangement is always in parallel. This ensures that if any one of the N inputs goes high, at least one conduction path is established to ground, and the output is driven low. This is consistent with the logical behavior of NOR, where the output becomes 0 as soon as any input is 1. On the other hand, in the pull-up network made of PMOS transistors, all inputs are connected in series. This implies that conduction towards VDD can only occur when every single input is at logic 0. Only under this condition is the output driven high. This series configuration reflects the requirement that NOR outputs a 1 only when all inputs are low. However, when extending to larger input counts, say 4-input or 8-input NOR gates, practical considerations come into play. For example, the series connection of multiple PMOS transistors significantly increases the effective resistance, thereby slowing down the pull-up process. Similarly, parallel NMOS devices reduce effective resistance, allowing stronger pull-down but at the cost of increased area. To maintain performance, transistor sizing adjustments are often required. PMOS transistors in particular may need to be made wider to compensate for the added resistance. Thus, while the logic structure is straightforward, the electrical characteristics of N input gates demand careful sizing and balancing to ensure both speed and power efficiency are preserved. Building upon the NOR gate configuration, we now move to the design of the CMOS N-input NAND gate. The NAND gate essentially mirrors the construction approach of the NOR, but with the pull-up and pull-down networks interchanged in terms of series and parallel arrangement. In the pull-down network, we use NMOS transistors connected in series. This series arrangement means that a conducting path to ground is only established when all N inputs are simultaneously high. Hence, the output is forced low only under the condition that every input is 1. Conversely, in the pull-up network, the PMOS devices are placed in parallel. This ensures that if any one of the inputs is low, at least one conduction path to VDD exists, pulling the output high. This satisfies the logic of the NAND function, where the output remains 1 for all input combinations except when every input is high. From an implementation standpoint, as the number of inputs increases, challenges arise. The series NMOS chain in the pull-down path introduces significant resistance, which directly impacts the switching speed, particularly during the transition from high to low. To compensate, designers often need to increase the width of NMOS devices, but this comes at the cost of higher capacitance. On the PMOS side, while the parallel configuration ensures strong pull-up capability, the total area increases as more devices are added. Thus, while the logical structure of the NAND gate is conceptually simple, scaling it to higher input counts requires careful trade-offs between delay, power, and area. This is a critical aspect of digital CMOS design, especially in complex logic circuits where multi-input NAND gates are frequently used in synthesis. Having analyzed the individual structures of multi-input NAND and NOR gates, it is important to compare their performance characteristics to understand why designers tend to favor one over the other. Both NAND and NOR gates rely on series-connected transistors in one of their networks, and it is this series connection that introduces delay by increasing effective resistance. In the case of the NAND gate, the discharging path lies through the NMOS pull-down network, whereas in the NOR gate, the charging path lies through the PMOS pull-up network. Now, when we consider device physics, the resistance of a conduction path is inversely proportional to the transconductance factor, denoted as 1/K. Since electrons have significantly higher mobility compared to holes, the transconductance Kn of NMOS devices is larger than the transconductance Kp of PMOS devices for the same geometry. This translates into a lower effective resistance for the NMOS pull-down path than for the PMOS pull-up path. As a direct implication, if we size the NMOS and PMOS devices equally, the NMOS chain in the NAND gate is able to switch faster than the PMOS chain in the NOR gate. This makes the NAND gate not only more efficient but also more reliable when implemented in performance-critical digital circuits. This is precisely why CMOS NAND gates are preferred over NOR gates in practical VLSI design, especially when logic synthesis tools map Boolean expressions into transistor-level implementations. NAND provides superior delay performance, better noise margins, and overall higher efficiency, which is why it forms the backbone of most digital standard cell libraries.